A few months ago I posted a series of videos in which I modified this T-962A infrared reflow oven, and during that series I took the oven from a condition where it wasn't really that useful at reflowing boards. The temperature profile couldn't be adhered to, the spread across the chamber was way too high, and it made it very difficult to try and get any decent results out of it. So after the modifications, I've shown this oven in use a few times since then. I'm getting excellent results with it now. It adheres exactly to the reflow profile that I program. Doesn't matter what I program in, it follows the profile faithfully and predictably and repeatably, so it gives me extremely good results. One of the things that I was trying to achieve with this wasn't just to get it to follow the profile, but also to even out the temperature spread across the chamber. So it wasn't really just a case of looking at the firmware and trying to modify that. In fact, I didn't modify the firmware at all. I didn't modify the electronics other than to fit a voltage regulator, which I'll come back to in a few minutes. So it was really just the mechanical approach that I took, because with an oven like this, then if you don't get a good mechanical layout for your cabinet, no amount of clever firmware and updates is really going to help that much. You're still going to be left with the same problem. I've since had quite a lot of inquiries and questions about what modifications I ended up putting into the oven, what size fan, that sort of thing. And I didn't give any details because it kind of depends on which modifications you make as to the size of the fan, the baffles, etc., because they all work together to give you the final profile. But I thought what I'd do is just briefly outline what's in this oven, and then if you want to, you could use that as a starting point for your own experimentation. I think even if you just followed what I've done, then it would still result in a huge improvement in the performance of the oven. Some of the modifications are not particularly critical. I did optimize mine for this particular oven, but to be honest, the bulk of the gain was fairly early on with some fairly simple changes. And even if you only get close to optimal for your particular oven, then it should still be a huge improvement, and it really does make these ovens actually usable. Okay, so other things that have come up in conversation are, I mentioned the flicker standard, and it doesn't really apply to me because I'm not selling these, but what I was really getting at is that the manufacturers of these, if they're at all interested in the flicker standard, which they're probably not anyway, but if they're trying to meet CE marking requirements, then they would have to take that into account, which would restrict what you can do with the firmware. You can get around it by changing the way that the heaters are controlled, the way they're switched. But bear in mind, this is an infrared heater and it's designed to heat the board. It's not designed to heat up the air in the chamber, and this is one of the things to bear in mind if you want to start modifying one of these. You're not trying to control the air temperature in the chamber. What you're trying to do is use an infrared heater to heat up a board directly. That's the only way you can get a profile that's fast enough that you can control. For the infrared heater to work, the heaters have to be above a certain temperature. If they're below the temperature that the infrared profile requires, you'll just end up baking your boards rather than reflowing them. So there is a very important distinction there. So pulse width modulation control of the heaters, it's not a good idea, because if you just have warm heaters trying to warm up the air, yes, it will warm the air up like a normal oven you'd cook in, but that's not what you're trying to do here. But as ever, experiments. If you want to try something different, then by all means go ahead, but I'm just going to detail here the steps that I took and why I did the modifications that I did. And if you want to follow and give it a go, then please do so. So first steps were to make an instrumentation board, which I did. I won't go through all the steps as to the testing I did. It was very extensive. I did probably 150 hours of testing using lots of different ideas and profiles. I even tried putting in what are mounted to a conveyor system in here. You can't just simply rotate the board, because the centre of the board wouldn't be moving and the outside would be spinning at quite high speed, which means you get a very weird profile. Also, it's the profile I was trying to control as well as the spread, so those two things combined meant I had to make some fairly fundamental changes, but some ended up as fairly minor in terms of what you needed to do in terms of modification. So first thing was to seal up the chamber. It had lots of holes in it. Big hole at the front where the drawer met the chamber. There were some big holes on the side. If you want to see how I went about resolving those, then go back and look at the initial videos on this where I modified the chamber. But it was really just taking some stainless steel shim, bending it to the right shape and spot welding it to the chamber. Now you could use screws or rivets or whatever you want, or even tape, but I just spot welded it because I've got a spot welder and it's the easiest thing for me to do. So the next main modification was to seal the drawer itself. There was a lot of leakage around here, and you could feel that when the machine was running. There was a lot of heat coming out of here, and you could also see the reflow paste smoke coming out of here when it was running, so you could see it was leaking everywhere. And that's not good. In theory it shouldn't make that much difference, but the problem is, unless you're in a room where there's no draft and all the windows are closed, you'll get variable results, because it doesn't take much airflow through an oven like this to disrupt the process. If you're getting air coming in from one corner, that board in that corner is going to be very cold. And bear in mind that the underside of this oven is almost completely open. So the first thing I wanted to do was seal the drawer. So I put a baffle in at the top of the drawer. What that's doing in there. So there's a baffle down here. I'll just move the camera so you can see it a bit more clearly. So this is the baffle. It's just bolted to the drawer front. There are some screws on here already that hold the front of the door to the bottom of the chamber. So I reused the screws. I made up an L-shaped bracket, just a piece of aluminium that I bent into a right angle, and then I bolted that to the front of the drawer. And it's in a position where this top edge fits snugly underneath the front edge of the inner chamber. So it's not this bit, it's the bit inside that forms the chamber lip. And so when you close it, you can actually feel the resistance, and that's now a very good seal, and it prevents air leaking out. That does make a big difference, stopping air getting into the front of the machine. Okay, so that's the first modification. The next one, it's a bit harder to show, so I'll do a few sketches as I'm going and explain all the various parts that I fitted to this. So I'll just move the camera again. Okay, so if we look inside the chamber, then at the back of the chamber there's a big fan. These things are getting a bit annoying. But what we need to do is, when the fan comes on, we don't want too much air blowing across the surface of the board. So what I did is fitted a baffle plate in front of the fan where it is open into the chamber. So I'll just do a quick sketch of that so you can see exactly what I mean. But I made it from a 0.5mm thick stainless steel sheet, especially shim stock. And again, I spot welded it to the back of the chamber wall. But if you wanted to, again, you could use nuts and bolts or rivets or whatever's more convenient for you. So I'll just get a piece of paper and show you exactly what I did. Okay, so at the back of the machine you've got the fan inlet. So there's a large cooling fan, and then there's a grill in front of it, and then air blows through the grill. Your board's sitting here. So the problem is, it's a big fan and it blows a lot of air into the chamber. And when the machine goes into cooling mode, then it causes a very rapid dip in temperature, and that causes the heaters to come back on, and you get a very poor finish to the profile. On top of which, there's a lot of open space in this grill, so when it's in the heat mode, a lot of heat is escaping out through the back of the machine, which you don't want. So what I did is fit a baffle plate that is just sitting in front of this grill. If I draw it side on, you have the fan. This is the rear of the machine. You've got the fan blowing in through the chamber wall, and the grill kind of sits like this, and the baffle plate was just attached like that. It's a flat piece with a slight kink at the top edge, and so it's bent like this, and it was spot welded here at the top, and it's about 2/3 to 3/4 the width of the chamber, so air can come in, goes around the edge, through the bottom, on the underside of the tray, and it prevents air blowing directly onto the board, and it also prevents hot air escaping during the heat part of the profile. So that made quite a bit of difference. It helps with the profile during heating, and it certainly helps and gives the controller more authority during the cooling part of the process. So that's quite an easy one to do. The bottom edge of this, of course, needs to be just above the level of the drawer. So it's not sitting behind the drawer, it sits just above the level, and then air can come down and mix between going into the drawer and down behind the drawer. So you're trying to get air to mix, you're trying to avoid laminar flow of the air. You don't want air blowing in bulk across any part of the machine. Okay, so that was that modification. So so far we've got the front seal plate and this rear baffle, as well as sealing all the holes in the chamber. The next modifications were a bit more involved and took a bit more work. So firstly, the baffles. So inside the machine, if we look, imagine we've got an X-ray and we look inside the machine, it looks like this. There are a series of 4 heaters. Let's draw 2 of them, and they're shining infrared energy down onto the board. And the problem with this is it means you get a hot spot underneath the 2 heaters, and that causes local hot spots on the boards as well. And because if we look side on, you've got the heaters are shining down, you get kind of a radiant pattern that looks like this. They actually overlap in certain places. Now if the heaters were the right spacing, the right height, the overlap might be enough so that where the heat does overlap, you obviously get an increase in energy, but that's not the way this chamber's arranged. That wasn't really working. What we needed to do was create a shadow underneath each of the heaters to cut down the energy that's going directly down onto the board. And it didn't take much. All I ended up with was a piece of stainless steel wire, 1mm diameter stainless steel wire, and it was stretched across the chamber. So if we now imagine we're looking side on to the heater, or from let's say from the front, then the heaters go through the side walls of the chamber, and all I did was attach a piece of stainless steel wire directly underneath the center line of the heater. So it's kind of center line of the heater, directly underneath, about 10mm down from the heater. So it's 10mm down. If you just suspended it like this, then it would sag when it heats up. So what I did is I put a tube on the outside of this and then a spring. So the one end of the wire, one end is just fixed, but the other end of the wire is on a small spring. It's only short, it's about 1/4 of an inch long spring. And what it does is it puts the wire under some tension. It's not a lot, but also it takes up the slack when the wire heats up. And obviously when it cools down, it keeps the wire from stretching and sagging. That doesn't make that much difference if you don't want to go to that trouble. It only makes probably 1 or 2 degrees centigrade difference, but I do have it in this machine, but it's not essential. Don't go too low with the wires, because obviously this is in the working space of the unit, and don't go too close. If you go too close, they won't really do anything. Okay, so that was the second modification. Now the main modification, the one that made the most difference, was moving the 2 sensors, or at least moving one of the 2 sensors. There are 2 thermocouples in this oven that pick up the temperature, and the oven seems to use the average of the 2 of them to control the heaters. One I felt was in the wrong place, so I moved it as part of the following modification. So this modification is a bit more involved. It's not difficult to do, it's just a bit more involved and took a bit of thought. So I'll just move the camera. I don't think we can see inside the chamber, but I'll move the camera so we can have a a quick look as to what I'm trying to describe, and then I'll draw it in a bit more detail. So on the underside of the heating element, what we have is the main problem with this oven. It's a real nuisance. On the underside of the heating element, what we're trying to do is avoid the hotspots that are caused by the heaters being in very defined lines. There's 4 heaters and they give heat that is very directional in terms of where the board is closest to it. You're going to get far more heat than where the board is more distant from the heaters. And so what we're trying to do is even out those hot spots, and rather than trying to produce more heat in certain parts of the chamber's got plenty of power, it just needs to control it. So rather than trying to produce more energy and heat certain parts of the chamber more, what I decided to do was try to cool the hot parts. And to do that, I decided firstly I needed to move one of the sensors. The profile wasn't being followed because the oven was trying to control the air temperature in the chamber. So what I ended up doing was moving one of the sensors. So inside the chamber originally there were 2 sensors. One was located in the center and one was located forward of center. And looking side on, if we have the heaters at this height, then one sensor extended down about 20 millimeters below the level of the heaters, and the other one was just slightly higher. And the heaters are located like this. So this one I left where it was but lowered it, so it's now about 5 millimeters lower than it was, so it's not quite as close to the heaters. And the other one I moved, so it's now in a tube. So there's a tube extending through the side wall of the chamber, and it comes in so that it's halfway between the side wall and the center line, so it sits about here. And then the sensor is passed through the tube and it extends about 15 millimeters outside the end of the tube. So this is just stainless steel tube, very similar to the tube that the original sensor was in, it's just a bit longer. And then this is just the same sensor. As I say, the other sensor was left where it was. The hole in the center was then reused, made slightly larger for the motor drive. So I wanted to move the air around inside the chamber, and this is where I got the biggest gain when I was making the modifications. So what I did is I fitted a fan. Now you're limited on the size of the fan that you can fit, of course, because you do have this sensor. If I redraw the chamber, that's the center. No, of course we've got the chamber out here. And we have this forward sensor, so that's the maximum radius you can have for the fan. And for the fan profile, what I found was we don't want to circulate a lot of air. What I wanted to do was to create a lot of turbulence, but slow moving turbulence. I didn't want it to be blasting and blowing air around the chamber. So what I ended up with was a fan blade that looks like this. This is just a copy, so exactly the same as what's fitted into this machine. So it's a bit of steel, and it's bent so it's very nearly at right angles. So we've got the center section and there's a single screw that comes through the center section and screws to the extension shaft I made for the motor. And then these 2 sections are up around about 88 degrees, so very nearly vertical. They do create a bit of upward airflow, so I didn't want to blow it down, it's coming up slightly. But the important parts are at the end. So if you imagine drawing a circle that's the diameter of this fan blade, call it a fan blade, it's not really a fan, then taking a section, so if you imagine you draw like this and then follow the circle around, that's this part. So you've got this straight piece, this part is following the circumference of the circle, and then it kicks out at the end at about 30 degrees. So, and it spins that way. Okay, so this actually spins as if it's going this way. And what this does is it creates a huge amount of turbulence off the end. It doesn't spin very fast, it's only spinning about 300 RPM, so it's going around quite slow. But what it's doing is it's kind of blowing air out a little bit, but it's mixing the air up in the chamber, and this makes a huge difference. You wouldn't think it'd make a lot of difference, but this is what makes the most difference. It's mixing up the air, it's making sure that the sensors, both sensors, are subject to a mixture of air, so it's not just the radiant heat from the heaters, it's measuring air temperature, so it's controlling through air temperature, but it allows you to control the infrared profile. To get this to spin at the right speed was relatively straightforward. So all I've got, again, side on, cheap motor. So these are the sorts of motors you get in Christmas decorations, this sort of thing. This is a 6-volt motor. It's got a 2mm shaft, 2mm diameter. So I made up an extension, which was just a piece of brass that I machined. A couple of grub screws at the top to hold it to the motor shaft, and then the bottom part was closed, so I didn't drill all the way through. And then I tapped this M2 and used an M2 screw to essentially bolt this to the bottom of the shaft. And all I did then is make up a couple of spacers that are used to secure the motor to the top of the chamber. The spacers are just to keep this motor away from the very hot chamber surface. And then, of course, there are a couple of screws that went through, and the whole thing is held in place. And then finally, there is just a fibre washer that sits on the top of the chamber around the shaft that goes through the chamber itself. So it's quite difficult to explain, but if we say this is the shaft from the motor, and this is the hole that's in the top of the chamber, then there's a fibre washer that just sits loosely. It's a relatively tight fit on the motor shaft. It's not a push fit on it, it's just fairly snug, and that turns mostly with the motor shaft, but it's free enough so it can just fall down onto the top surface of the chamber, and it just effectively seals this hole to stop air blowing out, and that's mostly to protect the motor rather than to affect the profile. And then of course the fan just sits on the bottom here. The fan is positioned above the heaters. I keep calling it a fan, but it's not really a fan blade. As I said, it's important to understand this is not trying to circulate a lot of air around the chamber. This is just mixing the air above the heaters and creating a bit of circulation. Okay, so once that's in place, the only other thing I needed to do was to fit a regulator to keep the speed of the fan constant. I used a 6-volt motor and a 3-volt regulator. The 3-volt regulator was connected to the main control board in the unit, and I just found the 5-volt regulator, found the input to that, fed that into my 3-volt regulator, and the fan is then fed with a regulated 3 volts to keep the speed constant. And then I just adjusted the size of the blade until I got the results that I wanted, and by adjusting the size I could adjust the speed it rotates at, and then by modifying the width I could also adjust the speed and determine how much air was being thrashed around with this. And that's really what it's trying to do. It's trying to act a bit like a food mixer. It's trying to sort of thrash the air around above the heaters and give you a good circulation. Okay, so that's pretty much it. That's really the only modifications I made, and if you look at some of the videos I've posted since about the performance of the chamber, and you'll see that not only does it follow the profile very accurately that's programmed, but also it gives a very consistent temperature across the chamber, and that was one of the main things I wanted to try and achieve with this. As I said, when I first got this, the temperature spread was very high and it was causing a lot of problems. This is the only downside with this, they really need to sort this out. And it was a temperature spread across the chamber that was causing most of the problems. You can get around the profile to a certain degree, but when you're getting a huge temperature spread across the chamber, there's nothing you can do. So that's really what I focused on sorting out, and that's what these modifications were really aimed at. It was to try and even out the temperature across the chamber, because it really was causing some major problems. And if they can just sort out the final problem, which is this, it gets a bit annoying after a while, then I'm pretty sure this will be a very usable oven.